Hello, my name is Mark Mller. I'm a PhD student at ETH Zurich, and today it is my great pleasure to present you our joint work on PRIMA, a general and precise neural network certification framework that leverages scalable convex Hull approximations. Let me first outline neural network verification. We encode a precondition using a convex abstraction of the input and then propagate this abstraction through the network to obtain an over-approximation of the network's outputs, and then reason about this abstraction with respect to a given postcondition to determine whether or not it is satisfied. With the typically used abstract domains, we can capture all affine layers exactly. What remains challenging, however, is to capture the nonlinear activation layers. Developing precise yet scalable such abstractions is what we address in this work. Until recently, neurons were only considered individually when constructing these abstractions. While this yields very scalable approaches, their precision is fundamentally limited by the so-called single neuron convex relaxation barrier. It is defined by the convex hull of the activation function given a neuron bias lower and upper bound to its input. More recently, it was shown that considering all neurons of a layer jointly yields much tighter abstractions. However, the involved convex hull computations have exponential complexity in the number of neurons in the layer, which makes them computationally intractable. Singh et al. Go one step in this direction by considering few small groups and computing the convex hulls for the input-output regions of these groups. However, they use expensive exact convex hull computations, which limit their framework to only considering few groups, reducing the achievable precision. We, in contrast, propose to use over-approximate convex hull computation method, which allows us to consider much larger numbers of groups, which can be chosen to overlap in a way to yield much tighter overall abstractions. So how do we efficiently compute these multi-neuron abstractions? Let's consider a case of a two-neuron layer where we have an input space that is illustrated here in x1, x2 space. We partition the space into its orphans where we have exact bounds on the activation function. Now we extend these regions from the x1, x2 space, which is just the input space, to the x1, x2, y1, y2, so input-output space. And then we there apply our exact bounds to obtain exact abstractions on these orphaned regions. Now to obtain an abstraction on the whole input region, we compute their convex hull, as illustrated here. However, this computation of the convex hull is computationally very expensive. So we suggest using over-approximate method as follows. We build on the so-called double description method, translating our original polyhedra from primal space to dual space, there intersecting them, and then translating the intersection back into primal space. How exactly we do this intersection will follow now. The double description method starts with, in this case, hexagonal region and then intersects it with these three constraints by first computing the rays from every point satisfying a constraint to all the points not satisfying at least one constraint. As you can see, doing this iteratively multiple times, we discover a lot of vertices which we then have to discard, checking for redundancy. And this can lead to, in the worst case, exponential growth of the number of vertices, at least in higher dimensional spaces. We instead propose doing batch intersection, so we add all constraints at a time and only do this so-called ray shooting process once. Doing this, in this case, we miss this corner vertex, but discover all other vertices and obtain this under-approximate intersection. Using this method to compute convex hulls and comparing this against the exact method for cases we encounter during neural network certification, we have about 70% reduction in the number of constraints we obtain, but only increasing the volume of the obtained convex hulls by 5%, in contrast to using single neuron relaxations, which would increase the volume by 400%. All the while, we are about 200 times faster. So how does this translate to verification performance? Compared to K-poly, so the predecessor method, and opt-C2V, a different approach to computing multi-neuron constraints, we are more precise in all cases and additionally faster in most of them. Thank you very much for your attention. I'm looking forward to chat with some of you in person at Pschel and also give a more detailed presentation there. Thank you and goodbye.